Hello, this is Dr. Liu. In this video, I will review these three questions, chapter 3 questions 1, 2, and 4. These are all the questions regarding entrance pupils and exit pupils and how images show up. So let's take a look at question 1. Okay, so I'll read the question content. An object measures 2 centimeters high above the axis of an optical system consisting of a 2 centimeter aperture stop and a thin convex lens of 5 centimeter focal length and 5 centimeter aperture. So the object is 10 centimeters in front of the lens and the stop is 2 centimeters in front of the lens. So that sounds almost like a camera. So the question is, determine the position and the size of the entrance and exit pupils as well as the image. Sketch the chief ray and the two extreme rays, these are the marginal rays, through the optical system from the top of the object to its conjugate image point. So we have a bunch of measurements that we need to first sketch. So these are all in centimeters, and the farthest distance would be 10 centimeters. So I could use the grid here, and each grid is a centimeter in here. So I'll do, that's 1 centimeter. Okay, so let's do object. Object is 2 centimeters tall, and here's 2 centimeters tall. So here's 2, and it is 10 centimeters from the lens. So let's count 10 blocks. Okay, here's the lens. We want to move that legend somewhere else. Maybe I'll move it down here. Don't think I'll need that space. Okay, so 10 centimeters. And also 5 centimeter aperture, that means the whole diameter is 5 centimeters. So that's 2.5. And there's another 2.5. So this is our converging lens. And then the aperture is 2 centimeters in front, so from here, and has an aperture of 2 centimeters, so 2 is that. Okay, so here's 2 centimeters, and this is 5, and the diameter is also a 2. Okay, so I'll draw an optical axis. Make this look easier. That line drawn through the middle. Alright, so the goal first is to find which one is the aperture stop, so we can image the aperture stop. Well, if the aperture stop is the lens, then it is just itself. It doesn't have, there's no other imaging element. So I guess the aperture stop is this hole here, this iris. To determine aperture stop, first we look at the angle subtended by the aperture stop at the on-axis object O here. So this is O prime on the top, right? So this angle, and then for the lens, we need to image it with the optical elements preceding it. Well, there's no imaging optical element preceding the lens, so it is just itself. So we're essentially calculating this and that. These are two different tangents. So let's use a different color. So this one here, we're going to calculate the tangent of that. And then at a slightly higher angle, we can see that because I drew to scale, so the angles are different. We're still going to calculate that. So that is from the iris. That's from the lens. Theta iris and theta lens. Okay, so tangent theta iris is the height, which is 2 diameter, so 1 in radius, and over that distance, overall this is 10. So let's write maybe number 10 here and number 8 here. So is 1/8. We can just compare tangent. We don't have to get the angles because tangent is it is a monotonic function. So theta of the lens. So we have 2.5 as radius, and then 10. So 0.25. Apparently this is smaller, so that gives a more specific angle to the cone of light. So that determines that the aperture stop is the iris. Okay, so that means the iris its image with the imaging element to the left or preceding it will be the let's write aperture stop here, will be the entrance pupil. There's no imaging element preceding this this aperture, so this itself is the entrance pupil. And then the exit pupil will be the aperture stop's image with imaging element behind it. So that's a regular imaging, light propagating from left to right. Okay, I think we have one more thing we need to put in was the focal length. So the focal length is also 5 centimeters. So I'll put the 1, 2, 3, 4, 5. I'll put that in there, F. Alright. Makes it easier if I have the focal points. So as we can see, the object is within one focal length. So its image is a magnified virtual image, and that's going to be over here. So we can easily calculate that. Let's calculate that in black. So we're looking for the image of the okay, so let's write it here. The image of the aperture stop to the right. So that is the exit pupil. So we'll have 1 over s plus 1 over s prime equals 1 over f, and the 1 over distance 2 centimeters, 1 over s prime equals 1 over 5. So 1 over s prime is equal to 1/5 minus 1/2. So 2/10 minus 5/10 over 10. So that's 3 negative over 10. So we have s prime is equal to negative 3.33. And we can also calculate the magnification, which is negative s prime over s. So that is negative of a negative 3.33, then divided by the s, which is 2 centimeters. So 1.67, so 67% of transverse magnification bigger, basically making things bigger. All right, so let's draw this. Distance 3.33, so that would be 3, so that's the third, and then 1.67, 67% bigger, so 1 turns into 167, so roughly here. That's 1, maybe 67 somewhere over here. Okay, so that is the exit pupil, which is the image of the aperture stop through that lens in the forward correct direction. Okay, so now we have done this, and we have other questions about the image. So the question on the image: determine position and the size of the entrance exit pupil. We did that, and sketch chief ray and the 2 extreme rays through the system. Okay, so chief ray, that would be the ray that comes off the off-axis object. So that is aimed at the center of the aperture stop. not actual stop, actually the entrance pupil. So we'll use a different color. So here's a CH3 that goes through the entrance pupil. I'm just going to get my ruler in place. A bit off. Okay. Do a bit more perfectly. So that center, and then it's going to refract. So which way does it refract? Must be towards the optical axis. But imagine, well, which way it does it. So if it goes through, if this ray goes through the entrance pupil, the center of the entrance pupil, then it's going to refract, and then its backward extension will go through the exit pupil. So I wish I could show the ruler, but you can't see it. It's not a digital ruler. So the center of the exit pupil is right here. So that would fit the backward extension. So the backward extension that can be drawn like this. Through that exit pupil center, then this is the solid ray that actually propagates through. So the way to draw this is, first you draw this line here, and it goes through the center. The center is actually a location of this aperture stop object, and that its image actually goes through here. So this ray can be considered as this object's ray that comes out, and then it must converge at the image position, which is also the center. It doesn't converge there, it just has its backward extension going through there. So that's the CH3. And then the extreme rays are the marginal rays that just glance through the edges. So if you want to draw that ray, I'll draw one of them. So the top one, for example, this top one. So first, of course, this thing, object, its image is that edge, not the other edge, because the magnification here is positive. So you have an upright image. So that point's image is that. So I'm going to draw the marginal ray or extreme ray. So right here, through that point. So suppose I hit that edge, and then hit here, and then the ray should bend further towards the optical axis, further down, as if it came out of that image point by extension. So like this. Suppose if I draw this long enough, I could find the image of the object. I didn't draw the green ray long enough. That's okay. So the other extreme ray or marginal ray will be heading toward the other edge. So I'll use the same color. And then it's going to refract, and that ray is going to go toward the optical axis as if it came from that edge, this edge here, with backward extension going through it. Okay, looks like my green ray is a bit off. I know that I didn't really draw the best I could, so that green ray extends somewhere over here. Maybe I could cheat like this, so get that green ray a bit better drawn, so that all of them go through the same exact point right here. So that is our image. If I want it, here's the image. Looks right, it is upside down because we're over one focal length from the lens, and we're actually exactly 2 focal length from the lens. So we have an upside down exact same size right here. Okay, so I think I missed by a half a grid, but that's what you get for just drawing approximately. So again, the marginal rays, they are the rays that are cutting through the edges. So you go toward one edge, and then you hit some optics, and then you have to refract, and then it has to come out of the image location of that edge. That edge's image is this. So if it doesn't come up that location, its backward attention comes through that. So that's that. Okay, so that's question number 1. Alright, let's take a look at the second question here. In question 2, everything has been changed, but the arrangement is still object, there's an iris, and then there's a lens. So repeat question 1 for an object 4 centimeters high. And okay, let's start with the oops, 1, 2. Okay, 4 centimeters high. Let's get down here. 1, 2, 3, 4. So 4 centimeter high object. And we want it to be 14 centimeters from the lens. Okay, so 2, 4, 6, 8, 10, 2, 4. So here's the lens. And I kind of wonder why the object is actually off axis like that. Why is it not moved symmetrically around the optical axis? But that's how things are drawn here. So let's look at the lens. The lens is a thin convex lens, 6 centimeter focal length and 5 centimeters in aperture. So we have the same size lens. So let's go up to 2.5, down 2.5. So f is equal to 6. Okay, and we have this location is 14. So 14 centimeters from that origin there. And then we have a 2 centimeter aperture, same aperture. And let's see, thin lens. And the stop is 2.5 centimeters behind the lens. Okay, so 2.5 right here. And it is still a 2 centimeter aperture, so it's like this. So that will be 16.5. Okay, so let me draw the optical axis. I suspect that maybe not all the object gets to show in the image. Okay, so let's just designate this top area, the entire area for drawing. Alright, so first we want to calculate which one is the aperture stop. So the lens itself doesn't have any optical element to the left to image with, so it is itself to be compared, and I'll draw a blue line here to indicate this is the angle we're looking for, the effect of the lens. And the effect of the aperture is imaged through that lens, so the aperture will be actually a bigger virtual image aperture, because again we have a focal length of 6, so that's a 2, 4, 6. Here's f2, 2, 4, 6. f1. So this is within first focal length. So to image, and you have to use the imaging element prior to the this element, this aperture. So is that you have your image to the left, from right to left. Because if you were looking here, with an eye, you're looking, light rays are coming from right to left, and then you're receiving those rays. And then you see a bigger virtual image of the aperture. There's a bigger aperture, right? So light ray has to propagate from right to the left. So to do that, we need to calculate. Let's not use that space. Find the image of the iris. Uh-oh. The program crashed, whatever reason. Okay, so let's see how much we lost. We didn't lose too much. This program has questionable quality. Even the iPad version is more stable. I was able to draw a lot of things on one page than I was able to draw on this program. So we're looking for image of the iris through all the optics imaging element prior to it to its left through L. So here's the lens, here's the iris. Oops. Okay, so we must image from right to left. So the object distance, let's have a list, and object distance is equal to that distance, 2.5, positive, because we're going this way. So 2.5, and focal length is 6. So we can do the same exact calculation. 1 over s plus 1 over s prime equals 1 over f. So 1 over s prime is equal to 1 over 6 minus 1 over 2.5. So to find the common denominator, that is a nice integer, so 30. That's 5. Okay, is that right? Let's see. So times 2 is 5, then 5 times 6 is 30, so times 12. Okay. So negative 30 over 7. So having negative, that means the image shows up as virtual image. It shows up on the object side. The object side is actually to the right because we're going from right to left. So 30 over 7. Let's take a look at this. So let me get Python for all the calculations. 30 over 7 and 4.2. Let's do 4.29. So 4.29 right of the lens. Right of the lens, because we start from the lens. And the image is measured from the lens. So 4.29, that means here's a 4.25 is roughly here. So 4.29 roughly here. And we also need the magnification, which is negative, so S over here, negative 4.29 over object 2.5. So that's a positive quantity. Let's calculate that over 2.5, 1.71. So if this size is 1 radius, then it becomes 1.71 radius. So let's do a 1.71. So that's a 2. That's 1/2, 1.75. So that's good enough. So maybe here. Okay, so alright, it's hard to get that exact because I don't have finer grids. Okay. Alright, so that's that, and now we can calculate which element, this element here or that element here, has the smaller angle, and apparently it is still the iris. We can see that with a ruler. So this still has a smaller angle. We'll just calculate that angle. Okay, so theta of the lens, tangent theta of the lens. So lens, that is 2.5. So 5 across, 2.5 over 14. So let's see, 2.5 over 14 is 0.179. So okay, and tangent theta of the iris. So the vertical is the iris size, so that's 1.71 times the 1, so exact 1.71. And the horizontal apparently is longer than 14, so it's 14 plus that distance counted as positive 4.29. Okay, so I'll get a value of my Python. And it's 0.093. Okay, so apparently the iris is still the aperture stop. Okay, I'll put that in there, aperture stop. So to determine the entrance pupil, you image the aperture stop with an imaging element prior to it, to its left, which is this thing. So this is the entrance pupil. And then to find the exit pupil, you image this thing with imaging element to its right. There's no imaging element to its right, so this itself is the exit pupil. So you can imagine that if you look from this side, what do you see? You see this hole here is restricting the light from coming through at higher angles. So that itself is exit pupil. But if you look from this side, all you see is a magnified hole here that is restricting the light from entering. So okay, so we've gotten these, and the question continues. We want to find basically the same thing. We want to do object-image relationship and see how far the extreme degrees are going. So let's find the object-image relationship here for this object. We'll use black here. So we have 1 over 14, that's s, plus 1 over s prime equals 1 over 6. So 1 over s prime is equal to 1 over 6 minus 1 over 14. So I'd rather just calculate the numerical value out. I don't really want common denominators anymore. So 1 over 1/6 minus 1/14. So I have 10.5. Oh, okay. I didn't expect something simpler. So 10.5. Okay, so 10.5 is measured from here. So that's 14, and then it would be okay. So 2, 4, 6, 8, 10. So here's 10.5 or 24.5 from the very left. And what about the magnification? Magnification is negative s prime over s. So negative 10.5 over 14. So it's minified and inverted as we expected. So 0.75 negative. So that means the height of the image is negative 0.75 times the height of the object, which was 4 centimeters. So 3 centimeters down. Okay, so I just have enough space. I'll be hitting the derivations if I went a little further. So 3 centimeters down. Halfway between the grids, 24.5. Okay, so that's the image, but not necessarily the entire image shows up. So that's the point of drawing the CH3 and the marginal rays, is to kind of inspect whether we have this thing that can pass through. So let's draw the CH3. The CH3 should be aiming at the entrance pupil, which is here a virtual image. We still aim at that image. Okay, so let me draw a line here. Maybe extend that a little more, but that's okay. I only want to aim at the center of the entrance pupil. I didn't make it there because of the bending effect. I'll be bent down further. How much further? Well, up to this much, because this point is the image of that object. Or you can revert the relationship. They're conjugate points. So instead, it just bends this way, further down. So let me get my ruler ready. So it does that. And if I keep drawing, yeah, exactly, that's where it's supposed to go, exactly on the image, right? Okay, next we're going to draw extreme rays or marginal rays. So let's do the okay, let's see. So the top one, the one that's aiming at that point. Okay, is that a green? Okay, that's good. Okay, so it's gonna aim here. Now it looks like it made it through there. Just kind of trying to hit that point. Okay, so which one did it actually hit? Because of the bending effect, this line is going to bend downward, and through the image, the conjugate point, which is this point. And it helps to line up the actual image here as well. Okay, so that's the marginal ray. And what about the other marginal ray? Trying to hit this point at the entrance pupil. Okay, so let's do that. I think this time I have better accuracy because the numbers are more integer-like, so it's easier. Okay, trying to hit that, and instead went through that with a little bit of bending. Okay. Okay. So that's it. Looks like if you look at the marginal rays, the CH3 and marginal rays, everything kind of made it through. There's no issue of getting things caught off. So let me take a look at the solutions diagram. Okay, it looks pretty nice. Okay, 3 centimeters worth it. Okay, so that concludes the second question. And then question number 4 is a bit more difficult because it has 2 lenses and 1 aperture in between. So let's set up question 4 now. It doesn't want me to go further down. Okay. Alright, so let's read question 4. Okay, 3.4. An optical system centered on an optical axis consists of left to right, source plane, thin lens L1 at 40 centimeters from source plane, aperture A at 20 centimeters farther from lens 1, then thin lens L2 at 10 centimeters farther from the aperture A, and then image plane. So lens L1 has a focal length 40/3, diameter of 2, lens 2 has focal length 20/3, and diameter also 2. Aperture A has a centered circular opening of 0.5 centimeters in diameter. So, well, if you look at all these, it is rather difficult to do a drawing because the distances are dozens of centimeters, 40 centimeters, 20 more, 10 more, but the lenses are small. Diameters are only 2. And some other ones, the aperture is only 0.5. So the system will be difficult to retrace through because of the large disparities between the two sets of dimensions, distances versus the sizes. So the question is, sketch the system. Actually, sketching it only requires you to put the elements in roughly the right locations. We're not retracing. Question B. Find the location of the image plane. Okay, so that shouldn't be hard. You can do it either with imaging through each lens at a time, or you can do that with a matrix method. And then question C, locate the aperture stop and entrance pupil. Okay, so we're going to determine that, and likely it is going to be that the aperture is the aperture stop. And then question D, locate the exit pupil. Okay, and then we also want to locate some field stops and entrance window, exit window, and determine angular field of view. So let's see how far we can go with the first few questions first. So we'll just sketch the system, and well, with 40 centimeters in mind, maybe each block 40 and a 10 and a 20, so maybe each block can be 5 centimeters. So let's do that. So this is 5 centimeters. So we start from here, and our object plane, this is our object plane, it's not our object. Our object is on the plane. So then 40 centimeters, so 8 blocks. Here's the first thin lens. And then another 20 centimeters, so the 4 blocks. Here's an aperture stop, not drawn to scale. The aperture stop is only half a centimeter in diameter. Can't really draw that to scale. And then another 10 centimeters, that's 2 blocks. We have another thin lens. Alright. And then some distance later, we have the image plane. Somewhere, I don't really know where it is. So see, here's 0, 40, 60, 70. Okay, so we sketched the system. And the next part is we need to find the location of the image plane. So, well, how do we do this? There are 2 ways. I think I'll do both. The first way is to do intermediate and final images. So we'll do that. We'll put the focal length on here. Focal length is 40/3. This focal length is 20/3. So if I want to mark up where that focal point is, so let's see, 40/3 is 13, so that's 15. So maybe roughly here, and 20/3, so 6.7. So this 5, maybe it's here. Okay, all right. So of course the object is over 2 focal lengths away, so it's going to show up as an inverted and minified image between 1 focal length and 2 focal lengths away. So let's calculate that. So so 1/s prime is equal to 1/40/3 minus the 1/40. So it's 340/2 over 140 becomes 240. So 120. So s prime is equal to exactly 20 centimeters. So block-wise, 1, 2, 3, 4 blocks. So it shows up right here. This is where the image shows up, right in the aperture. Okay, so we also want the magnification, which is negative s prime over the s, so it is negative 0.5. So it's minified to 50% the transverse size. And then we want to do the second image with the same exact thing. This is L1. L1. So through L2, the object distance is that. 2 blocks, so 10 centimeters. So 1 over s prime is equal to focal length 1 over 20 over 3 minus 10 centimeter of object distance. So that is still away out of one focal length away. It's still going to show up as a real image. So this is 3 over 20 minus 1 over 10. So that's 2 over 20. Then you get 1 over 20 left. So it's 1 over 20. And s prime, so is equal to 20 centimeters. Very nice integer here. So 4 blocks away, here's s. Okay, that second image here. So we have determined the image plane to be 20 centimeters, so 90 centimeters from the object. So here's our image plane. All right. So that's our image plane, and the magnification in this stage, negative, so 20 over the object distance 10, so that's negative 2, and then m total is equal to m1 m2 basically, so negative 0.5 times negative 2, which is equal to 1. So it's right side up. I just want to move that down here. This is L2, so that's a total. Alright. So if you have an object here, it's going to show up right side up as an object over there. So let's see. Okay, so we locate that, and then we locate after stop. Which one is after stop? And the entrance and exit pupil. So let's just draw an object here. An image here, final image. Okay, the after stop. So from the object, on axis object right here, we need to determine which one is. So with this this lens, the size of the lens diameter is only 2, so it has a radius of 1. So I'm just going to draw this arbitrarily because the scale will never work if I draw to scale. So 1 centimeter. And here is a diameter of 0.5. Opening 0.5, so that half of it is 0.25 centimeters, and the other lens, lens 1, lens 2, diameter of also 2, so 1 centimeter in size. So if you look at these, well, it's not easy to calculate. So L1's role. This L2 aperture. So L1's role is, well, you can calculate the angle like this, right? But the aperture needs to be imaged to the left in order to have its image with size calculated, and L2 also needs to be imaged to the left using its image to calculate the size. But I think L2 is not the aperture stop, because something about that size image over here is going to get really close, so the angle is going to get really big compared to this, which is here. So that's my guess, but we need to calculate. So let's be specific what we're calculating. Imaging A through L1. So that's going to from right to the left. Okay. So through L1, so this is 1 over s prime is equal to 1 over f, so 1 over 40 over 3 minus 1 over object distance. So from right to left, this is object distance. 60 and 40 centimeters, 20 is the object distance. 3 over 40 minus 20 is 2 over 40. So I get 1 over 40. So S prime is equal to 40 centimeters. So 40 centimeters, okay, let's see where that is. So 40 centimeters from the lens, so that's right here. Okay, that's right there. And with a whatever size, then there won't be any limitation at all if you think about that, right? Because it's right here to calculate the tangent. Oh, that's this is at x equals 0. Let's call this axis. So x equals 0 is right here. It's going to be overlapping with the object, and we can calculate the size of it, but it really doesn't matter. So let's calculate the size of it. So the magnification is equal to negative 40 over the object distance, which is 20 negative 2. So this diameter is going to be, instead of a half, is a 1 centimeter. So I'll just draw something like this dashed line. So this is A's image. It definitely is not restricting. Okay, so what else? This thing itself has this 1 centimeter over 40 centimeter, so that's a pretty small tangent angle. How we can do that? Just by looking at this thing here. That's for L1. So tangent theta 1 is 1 centimeter over 40 centimeters. I'll just leave that as is. Okay, so let's consider the effect of the second lens. I think the second lens will not be the limiting factor either. If I think about that, this is how it works. The second lens needs to image through the first lens, but let's do that. So L2 through L1. This job seems like it involves a lot of applications of simple object-image relationship. You just have to apply it right every single time. The object distance is from 70 to 40 is 30. So that minus 30. So S prime is equal to, I'll just use Python. One over 3 over 40 minus 1 over 30. Okay, 24. Alright, very nice integer here. So 24. So 24 centimeters to the left of the imaging element L1. Okay, this is 40 centimeters to the left of L1 as well. So 24 centimeters. From here, 24, I'll have 16 left. So if each one is 5, 5, 5, 5, so here, roughly this location. And let's also calculate the magnification, which is negative 24 over, let's see, object distance was 30. So 0.8. So at this location, 0.8, so roughly here. It is a real image, so that's okay if I drew it with solid. So let's also add some arrowheads to limit the size of these lenses. Okay, so that's that, and apparently that angle is less, but we should calculate it. So tangent theta 1 is equal to, the vertical was the 0.8, so 0.8 high, and the horizontal is, I should mark this location as, I had 24, so the 16 over 16, so 0.0, let's see, 0.05, right? Okay, so I also need to calculate this. This is 0.025. Yep, and 0.8 over 16 is 0.05. Okay, so that tells you which one is limiting the angle more. It is F. It is the L1. So L1 is the aperture stop. Okay, so our next step, now that we have identified the aperture stop, we will need to find the entrance and exit pupil. The aperture stop has no imaging element to its left, so it itself is serving as the entrance pupil. And its image to the right is the exit pupil. That means its image to the right through the second lens. We haven't calculated that yet. So imaging L1 through L2. See, it's repeated use of simple geometrical optics, so that 1 over S prime is equal to 1 over, so L2's focal length 20 over 3 minus the distance. L2, L1 are 30 centimeters apart, so 1 over 30. So that gives me 3 over 20 minus 1 over 30. So that's what, 60, common denominator 9 minus 2. So okay, so eventually we're not getting any nice integers anymore, so it's 7 over 60, and S prime is equal to 8.57. From L2. Okay, so we got to keep that checked from where, so from here. So 8.57. So this is 5, 10, so 7.5, 8.7, okay, roughly here. Okay, so what about size? M is negative 8.57 over the 30 centimeters. Let's see if that's right. Yeah, 30 centimeters. So that would be actually the negative 60 over 7. That's what this number is. And over 30 centimeters makes it easier. So 2 7s. And still I need a numerical quantity. So 2 over 7 is 0.286. Negative 0.286. So the diameter prime is equal to 0.286 times the 2 centimeter diameter. So 0.571. Okay, and this radius prime is actually just the 0.286. Okay, so I had that as a 1 centimeter vertical, so that's a quarter, a little more than a quarter. That's it. So this is our exit pupil, and the distance right here, this is 8.57, so it is 78.57 location wise. and the size is that. So you can say, well, that is diameter 0.571. Okay, so that's our exit pupil. We have determined it. Okay, so now we need to locate the fill stop and entrance window and exit window. These are concepts I haven't really covered in the lecture yet, so I'd like to skip them and maybe come back with a separate video with this question already solved in the solved state, so I can add those into the discussion. Thank you.